This is lesson 19 of the A-level physics no nonsense, no thrills, certainly no thrills, just a whiteboard and me and a pen physics lessons. And this one's all about wave properties, at least the beginning of wave properties. So let's consider a common piece of apparatus that's used to investigate wave properties. It's called a ripple tank. Now, what the ripple tank consists of, and I'll do my best to draw a quick sketch of this. Let's label it ripple tank. My lack of capital R is going to be driving some people mad. What it consists of is a sheet of clear plastic with some sides on it so that you can have water in a tray. So there's some sides on this that I'm not drawing. Maybe I should try and draw them. Sides on this. Do you know what? Let's use a straight line tool. Why am I trying to make do with a wiggly line? So we're going to go with sides. That's better, isn't it? This is my attempt at a 3D diagram. So little sides coming up like that to hold the water in the tray. Just like that, something like that. Now you put a piece of card or even a mirror on the bottom if you want a mirror at 45 degrees so you can look at things from maybe the right-hand side. It doesn't really matter. The whole thing's got legs. That doesn't matter either. You have a light source. Let's use a circle for that. You have a light source at the top, emitting light. I'll label that in a second. And then you have something that can produce vibrations, some sort of vibration generator, which I'm just going to draw as a bar inside here, but it'll be connected to something that shakes the water up and down. So maybe it's got a motor on it with an eccentric cam and it's suspended on springs so it shakes around. Doesn't matter, some sort of vibration generator. So let's label the different parts of this now. So we've got transparent tray of water, transparent tray of water. We've got a vibration generator here. Should use a different color for these, shouldn't I? Never mind. Vibration generator. And we've got a light source. And there are some clever things we can do with the light source, like we can have it strobe, so it flashes, synchronized with the vibration generator. But we don't need to, we've just got a light source. And that's basically it. So the light is going to pass, let's use it as a highlighter pen. The light is going to pass from the light source through the tray and then onto the bottom bit there, through the tray and down into there. And we'll be able to see wave pattern on the table. Or if there's a mirror at 45 degrees, we can project that pattern somewhere else. So let's write down here, wave pattern. I think that's how you spell pattern. Just like that. And why will there be a wave pattern? Well, let's suppose that we've got water waves doing this. Any light, and you'll remember this from GCSE level, any light that is incident on the surface, perpendicular to the surface, and normal to the surface, will just pass straight through and it won't change direction. At least it won't have any noticeable change in direction. So you'll just see that. And any light that passes through here and through here is normal to the surface, so it will just pass straight through. Any light that passes through at an angle will be refracted towards the normal and end up over here. And any light that comes down, come on pen, any light that comes down here will be refracted towards the normal and end up over here. Any light from over here goes towards the normal and ends up over here, and so on and so on. So what you'll end up doing is getting bright spots and spots that are less bright. So this is bright there. This here is dull or dim. Let's say dim. This here is bright. And this here will be dim. And so on. So we get bright, dim, all the way along. So that's what we're going to see. And I could label these lines light, I suppose. Now, obviously, this is going to work better if the light rays are all parallel. And there are ways you can make that happen. But for the sake of our experiment, as long as the light is far enough away from the water, the rays are close enough to be in parallel that we can use them for our investigation. Let's label this one water wave. Water wave. So we've now got a way to investigate what waves do. And as I say, there are certain things we can do. We can use a stroboscope, which flashes the light. You can actually just use a piece of card or something with slits cut in it and spin it. If we spin it at the right angular speed, then it will mean that you only see, if you look through the card with the slits, you only see the pattern that has been formed underneath the ripple tank at certain instances in time. And if you synchronize that so that it corresponds to the time period of the wave, then you'll just see the wave pattern as though it's not moving. So there's clever stroboscopic ways of viewing these things. And why would you want to do this? Well, because it's going to allow us to see some of the properties of what waves do. What makes waves special, what makes waves unique, is that they can interfere. And that's basically it. The fact that waves can interfere, is the reason for all of the interesting phenomena that we see. Another way of saying they interfere is that they superposition. That's a technical term. Now, remember from last session, let's just go back to last session. We looked at the waves being displacements. Remember that? We started with that, and we said, but what is that displacement of? Well, it could be a physical displacement of matter, but it could be electric field strength, it could be probabilities, it could be all sorts of things. So now when we come to here, what do we mean by superposition and interfere? What we mean is we add up the effects. Displacement is a vector. And so if the wave, which is just influencing something, in the case of the water wave, the height of the water is influenced by the wave, we can add up the effects of two or more of these influences. So we can add up the displacement of the water due to one wave and due to another wave and due to another wave and so on, and get a resultant displacement. Now, with vectors at GCSE, you were quite happy calculating resultant displacements by using arrows for each displacement. And you might have had to add 2 or 3 arrows together. But here we're looking at something much more complex. There's an awful lot of bits of water that are being displaced in all sorts of directions. So the superposition of all those effects, you're adding together all those influences, produces the wave patterns that we see. And there are 3 that we're going to start with. 3 things that light, that sound waves, that mechanical waves like water waves can do. The first one is reflection. Reflection is a consequence of superposition. It is a consequence of interference. And so with reflection, what would we have if we looked on our ripple tank, or on the wave pattern under the ripple tank? Well, perhaps in the ripple tank, we could put something that reflects the waves, like a piece of metal sheet or something stood up that reflects the waves. And what we would see is that the wave fronts will be coming in like this, and they're all evenly spaced. Now, these wave fronts, they are lines where we've connected all the points in the wave that are at the same phase. Actually, the definition technically is that they've got the same phase difference, but that's a very minor sort of distinction there, which isn't tremendously important. So constant phase is one way of thinking about it. So we can say all the crests, we could say all the troughs, or we could say all the points where the phase difference is 30 degrees. Phase difference between the beginning of our wave and there was 30 degrees. It doesn't matter. We could say any of those. Remember, let's go back to the last session. We've got the crests, we've got the troughs. So let's just think about these as crests of the water wave. That might be the easiest way. These lines show you the crests of the water waves, and they form a nice line because our vibration generator was a nice line. And if we add up all the effects of all the bits of water that are vibrating, this is what we see. So these wave fronts are going to approach this reflecting surface like this. And they're not going to get through it. But what's going to happen is they're going to do something like this. And then we're going to see another one here. And then we're going to see another one up there. And so on. The wave fronts appear to change direction. Now, I could label the direction that the wave energy is being transmitted. That's this direction. And then after the reflection, it is this direction, like that. So let's use a key. Let's say red. And for some reason, it's not letting me draw it. Red equals direction. You can say the direction the wave energy is being transmitted. We usually just say direction of wave propagation. Or propagation. Wave propagation. Propagation of a wave just means sending the energy through that wave. And the blue ones, they're going to be our wave fronts in this little key, which we're defining as points with the same phase, or a constant phase difference. So same phase, such as all the crests, all the troughs, or all the points 30 degrees. Okay, so the waves come in, they reflect, they go out. Now, an important observation of this is that the wave fronts are always perpendicular to the direction of propagation. This is true. Wave fronts are always, I can't write today apparently, always perpendicular. That's perpendicular. It's a friend of Count Duckula. You won't remember that. Perpendicular. Count Duckula was a cartoon from the 90s or late 80s. Perpendicular to... Can't even write the word to. To wave propagation direction. I'm not going to bother writing direction. So that's an important point, and we observe that. Not only that, we also observe that the angle of incidence is always equal to the angle of reflection. I've tried to draw it so that the reflector is 45 degrees to the direction of wave propagation, but it doesn't matter if you change that, you'd see the same thing happen. Also, what you'd notice is that the wave fronts here and here and here are actually crossing, and so you'd actually get even, the wave fronts are where it's lightest on the screen, they'd be even brighter at those points. You get a sort of cross or a square pattern, a hash pattern from that. So that's reflection. We could talk importantly about how we measure the angle of incidence from the normal, but I'm sure that's going to come up a little bit later, so we don't need to dwell on that straight away. In fact, it comes up a lot when we talk about optics, and we're just focusing on waves at the moment. So yeah, let's not get into specifics like that too much at this stage. What else can waves do? They can refract. Refraction. Now, refraction is caused by a change of speed of the wave. And we can see a change of speed in the wave if you take the water waves, if we make the water less deep. Now, you've got to be very careful with this experiment and usually have to reduce surface tension of the water by using some synthetic earwax or washing up liquid to try to see the effect that you want to see. But it is possible to show refraction with a ripple tank. And if you've ever used a ripple tank and struggled, synthetic earwax is your friend. So actually, you can even use real earwax, but I wouldn't recommend it. It's gross. So what we've got here is a boundary between two different depths of water. And our water wave fronts are coming in. Here they come, quite happily coming in, evenly spaced because the distance between two adjacent wave fronts is one wavelength. Looked at that in a previous lesson. Here they all come, evenly spaced. And then, oh no, they reach this sudden change of depth. Now, obviously, the water isn't suddenly higher. That wouldn't make any sense. The water would just fall if you tried to lift it up. So what's happening there? Well, the bottom of the ripple tank is raised a bit so that the water is shallower. So the top of the water is all continuous. The bottom of the ripple tank is a little bit raised. Now, if you do that, that has the effect of slowing down the water wave. Shallower water has slower waves in it than deeper water. It's not a huge difference, but it's enough that we can see the effect. So you will now see the wavefronts actually change direction. And not only do they change direction, they also appear closer together. Now that's interesting. Why are they closer together? And all of this we're going to get into. Might not be this session because this is an introduction to waves, really. What's it called? Wave properties. But like that. Now, the wave fronts are all still evenly spaced. And I've got to be quite careful when I draw the next one now to try to make sure that they are all evenly spaced. But they are closer together than they were before. Now, that makes a lot of sense if the wave is being slowed down. So we have our wave energy, the direction of propagation, being along here, and then it's along there. It's at an angle, and that's because it has been refracted. The wave has been refracted. But we can also see a reduction in wavelength. So we know that C equals F lambda. But we say that C is reduced. And that's only in this example. In another example, we might have a situation where the speed of the wave is actually increased. Maybe if we take water waves, we're going from shallow water to deeper water. Or we could be looking at a different type of wave, not a surface wave on the water. And so we could have situations where waves are made to speed up, waves are made to slow down. They're all supposed to be evenly spaced along here, but it doesn't look like they are very well. So maybe do a better job of your own diagram. When I look in the textbook, it's awfully drawn. So I think I could be forgiven. So if C is reduced, then therefore, this 3 dots there means therefore, lambda is also reduced. Now, you might be thinking, well, why not frequency? But let's think what that would mean if we had a reduction in frequency. If we had a reduction in frequency, then there would be fewer waves per second traveling on the right-hand side of the black line as traveling on the left-hand side. And remember the wavefronts where the water is, we're going to take them as crests, the water is higher at the wavefronts. But also remember that we're changing the depth of water by lifting the bottom, the seabed, if you like, the bottom of the ripple tank up. So the top of the water all has to have the same average height. So if you put all those ideas together, it would be impossible to have a situation where the wavefronts suddenly disconnect across the black line that I've drawn here, representing the step change in depth of water. If the water suddenly changed depth, that can't cause a wave front to terminate all of a sudden, and maybe a space after it where there is directly between two wave fronts, because directly between two wave fronts is a trough. So you would have this imaginary barrier between the water being higher on one side and the water being lower on the other side of this step change in water depth. And of course, you would see the water progressing and all the rest of it. Now, that means the water would be somehow being held back by an invisible line and prevented from falling from the crest on one side of that black line to the trough on the other side. Okay, so I mean, I'm just going to do a quick sketch, freehand sketch, to get the idea of this. Here's the barrier, here's the wave fronts coming in, and imagine if afterwards the wave fronts were like this. Well, what would that mean? If we just look around this part here, you've got a wave front on the right, and yet there's exactly between a wave front on the left. So you would have a situation where the water would be being held back all by itself and prevented from falling across that invisible barrier. Now, that has happened in history. There is a historical record of that happening twice. The first time it happened was when Moses crossed the Red Sea. And given that that involved the intervention of God, I think we're safe to say that that's not a normal situation. The second time in the historical record when it happened is in the film Moana. And I'm not convinced that we could say that that can be used as scientific evidence for the normalcy, the normal situation where the wave fronts can become disconnected across a boundary. No, the wave fronts cannot become disconnected across a boundary. It wouldn't make sense, which means we have to have the same number of waves crossing the boundary, say touching the boundary from the left-hand side, as I've drawn it here, as crossing into the right-hand situation per second. We have to have the same number of waves per second hitting the boundary from the left as leaving the boundary from the right, which means the frequency on one side must be the same as the frequency on the other. So let's just write that as because f does not change. So then you've got to think, well, why does a reduction in wavelength mean that the wavefront changes? And the why is a difficult question to answer. This, by the way, is not a very good explanation of why. There are some fantastic explanations out there on the internet, but I do not want to get into them now because this is really just a quick series of lessons for A-level, the sort of bare bones of what you need to know. So if you're interested in that, do search for the sort of PBS videos. Can't remember the name of the chap, but it will come to me later, where he explains why refraction happens. They're very good videos indeed, and it's much more subtle and complicated than what we're talking about here. What we're talking about here is a geometric observation that the only way to get the wave fronts all lined up before, the wave fronts all lined up afterwards, and yet the wave fronts closer together afterwards is for the wave fronts to change direction. This is the only way geometrically we can produce this effect. Oops, wrong pen. The only way we can produce this effect geometrically is for the waves to change direction. That doesn't say why it happens. It's just an observation of what we see. So when the wave gets slowed down, we refract towards the normal. So let's draw a normal on this now. And when the wave is sped up, it refracts away from the normal. So there's our normal. And as soon as I add the normal, it becomes obvious what I mean by towards the normal. Normal being 90 degrees to the surface. In this case, it's a boundary, 90 degrees to the boundary between two different depths. You can see that the red arrow coming in is further away from the green line than the red arrow coming out. So we could label, let's use orange for this, we could label this as maybe theta I, theta representing an angle, I because it's incident, and we could label this as perhaps theta R for refraction, but I'm going to use T for transmission because I don't want to get R confused with reflection. And so you can see here, if the wave slows down, then theta T is less than theta I. And we better probably label that theta T equals the refraction angle and we can say that theta I is equal to the incident angle, or the angle of incidence. Let's write it as angle of incidence. Angle of incidence. And these are just normal English words. Incident, coming in, touching, making it happen. Right, so that's refraction. That is what we observe, and that is why we observe it. We also see refraction with light. We see refraction with sound. Or maybe I should say we hear refraction with sound. This is normal. Pun not intended. The other phenomenon that we can observe waves doing is called diffraction. Sometimes pronounced diffraction, in particularly some parts of the world. We tend to pronounce it diffraction. Diffraction. Oops, handwriting's terrible. Diffraction. So what is diffraction? Well, at the very basic level, you could say it's the spreading out of the wave. That's certainly how you might learn about it in GCSE level. You might learn that diffraction is caused by a wave, perhaps passing through a gap and spreading out. I don't think that's a satisfactory explanation or description of what diffraction is, but it's a good starting point. So if I have, for example, a gap like this, and I compare it to a much wider gap, this is going to be an interesting comparison. And I have my wave fronts coming in, and I'm going to freehand this, so wish me luck. And we've got my wave fronts coming in here, like this. Then after they've passed through this gap, they are going to diffract. They're going to spread out like this. Whereas in this situation, if I've got exactly the same wavelength of waves coming in, so the distance between wave fronts is exactly the same, doing my best, draw that one there, then we are going to get diffraction, but it's going to be far less of a diffraction angle. Oops. And I could label some of this stuff. I could say, look, there is where the wave is, well, that's not even symmetrical. That's not even close to being symmetrical. And there we've got this. So you can clearly see there's a smaller diffraction angle when the gap is wider. That is an observation that we can make. But why does the wave spread out when it goes through the gap anyway? Well, it spreads out because of superposition. And within the gap, we can imagine it to be an infinite series of infinitesimally spaced sources of waves. And when we add up all those effects, what we see is this diffraction effect. So maybe I should label this with small, this is the bottom of the page, so small gap, colon, big spread. Oh, it's awful notes. Large diffraction angle be better. And this one here is going to be big gap. And this is relative to the wavelength. Small spread. Now, you've got to believe that we're going to be talking about diffraction in a lot more detail later on. But this is the general example of what diffraction is, this apparent spreading of the wave. And I'll leave that there. There is some discussion that can be had about how you can use all three of these ideas, maybe not refraction, but how you can use reflection and diffraction together to design things like satellite dishes, where you want them very large so you can get a lot of waves in, but then you've got to be careful, because if they're too large, then you get very little spread, which means you've got to aim them a little bit tighter, aim them a little bit more carefully at the target. And the dish itself has to be curved so that you reflect those waves to a point where they've got a receiver. But a lot of that we don't really need to go into at this stage. We will be linking this to diffraction as a whole topic on diffraction in the optics section of this course. So we'll leave that for now. And yeah, that's the end of this session, all about, I can't remember what it was about, the beginning of wave properties. Now we're going to look at superposition and a little bit more information about superposition and what it is and how it works next lesson. So I hope I see you then. Bye-bye.